Hi all. This is going to be the third lecture of chapter 1 of Numerical Linear Algebra series based on the book by Trepton Lloyd. So, this concept is related to norms, which helps us to understand how distance between two vector in a vector space, how a size of a vector in an m-dimensional vector space can be defined and can be understood and can be intuited. And this also help us to understand how for example, an algorithm computing an approximation of the true solutions, how that approximation to the true solution, that yardstick between these two, from the approximate solution to the true solutions, can be helped and can understood and also to be measured through this concept of norms, and also helps us to understand the rate of convergence and how that iterative algorithm that we are going to introduce later part of the lecture series will converge to the true solutions using a numerical linear algebra algorithms. So norm can be two vector norm and matrix norm. First, the vector norm. Norm as defined, it's a function which it's a mapping an n-dimensional space to a real space, and it assigns a value for any m-dimensional vector, and it has to satisfy to define as a norm any function having following these three conditions. One is it only vector the norm can become non-zero only if the vector is a non-zero value, and it has to obey this triangular inequality, and also it has to obey like if it is scaled, vector is scaled, and it norms also scaled equally. So these are the p norm is much wider utilized norm, and these are the different norms. Like one norm is the sum of the maximum absolute values, and two norm, as we defined earlier, it's an Euclidean distance between 2 points, and the infinite norm is the maximum value, absolute value, and the p norm is a generalized norm which can define all these three things. So Euclidean norm is the specialized version of the P norm, and all its geometrical interpretations are given in the right hand side. For example, 2 norm is something like a spherical unit ball, which is measured in a spherical unit ball. And similarly, there can be a special norm called weighted P norms, where W is a diagonal matrix, where it scales every element of the vector X in based on the diagonal values of that W matrix, and that W diagonal weighted P norm can be defined as from the equation 3.4. And what it does is it transforms the unit sphere into an ellipsoid. So then we can also helps us to understand the generalized version of that weighted P norm, where W is not necessary to be a diagonal matrix. It can be in any non-singular matrix. In that aspect, it can go to an unweighted induced matrix norm. Now we come to understood about the matrix norm. One of the concept is what just understood that m cross n matrix to be as a single dimensional vector of elements mn, and we can apply any of these norms what we defined earlier, like for example Euclidean norm. But there is another special type of understanding this two-dimensional tensor using the concept of induced matrix norms. For example, we have X, it's a domain of matrix A, and if we are multiplying X, it ends up in the range of A. AX is a range of A, and this applying this concept, and C is the lowest value among the ratio of the AX by X, and this is called the C is termed to be as the matrix induced norm. And these are some of the examples which we don't go deep into that, and one norm of the matrix can be based on that induced matrix norm can be understood as the we can make a one norm for every column, and the maximum value of that one norm applied to every column will be the one norm of the matrix. Similarly, infinite norm will be the transpose. If we make a transpose of this matrix and make the same one norm to every column, and applying the maximum value of that column value will become the infinity norm. Then we have Cauchy-Squarce inequality based on the Haldor's inequality, equation 3.1 and 3.12. It's nothing but like we have PQ any value, and we put a P norm to this, and that this inner product will be less than or equal to this ideas. And once that case P and E equal to 2, it becomes Cauchy-Squarce inequality. So based on this idea, we can define a two norm. Two norm is nothing but a similar idea of applying a Cauchy-Squarce where x becomes a, then it will becomes like an Euclidean norm of that vector a. Similarly, if you put an outer product, then it will end up with similar kind of the matrix norm. Will be using the concept of Cauchy-Squarce inequality. We can define this relationship. So again, to define a matrix norm not necessary to be induced by vector norms. There only if that can satisfy as defined earlier has three conditions. One is triangular inequality, same like vector, and it has to be non-zero only if the matrix is non-zero, and also scaled by alpha is also scaled in the norm. So based on this concept, we can define a norm called Frobenius norm. It's same like using an Mn, unraveling the elements to an Mn values and putting a Euclidean norm, and that is defined to be as a Frobenius norm. And this also has some analogical properties defined as 3.1a, and in then again we saw that any unitary multiplication of a vector doesn't changes the orientation between two vectors, and also doesn't scale the vectors. It just only rotate the components. Similarly applies to the matrix norm. When we applying by a unitary or a orthogonal matrix, it doesn't changes the norm of the matrix. Same applies here, any two norm or a Frobenius norm. So these are the short, brief portions about to understand about what are the norms and how far we can utilize these norms to understand the convergence properties of algorithm that we are going to introduce in the later part of the lecture series. Thank you.